A very warm welcome to everyone. As you all know, we are doing video lecture series based on vector analysis, and today we are going to discuss Gauss divergence theorem. As you all know, we have already done the divergence mathematically. We have studied its physical significance, and in the previous video we tried to understand divergence in terms of Cartesian coordinates, which actually gave us the expression that how do we write and why do we write the divergence of a vector function the way we write it, its expression. We try to understand its expression both mathematically, and when we derived it using Cartesian coordinates, we actually got to know that what's the reason behind that particular expression. Today we are going to use that expression to understand one of the most important theorems in vector analysis, which is Gauss divergence theorem. In vector analysis, we have three main theorems. Three important theorems are there. One is Gauss divergence theorem, another is Stokes theorem, and the third one is Green's theorem. And today we are going to do one of them, which is Gauss divergence theorem. As the word divergence is already there, so that means we have to use divergence here. Whatever we have studied about divergence, we would be using those details. And the way we tried to understand divergence in terms of Cartesian coordinates, almost similar, almost totally similar derivation we would be having for this Gauss divergence theorem. So if you have watched previous video, which is divergence in terms of Cartesian coordinates, it would be really easy for you to understand this particular theorem and its derivation. And one more thing that we should always keep in mind is that whenever we talk of divergence, one thing is sure, that the two integrals out of the three, which we already know, line, surface and volume, the two integrals which would be used are surface integral and volume integral. Whenever we talk of divergence, these two integrals are involved, because divergence involves surface, and of course if something is diverging, spreading out, it might be spreading out in some three-dimension space, and then whatever surface we include, that would be enclosing some volume. Whenever we talk of surface, usually that surface does include or enclose some volume, and that's why whenever we talk of divergence, we have to consider surface integral and volume integral. So let's get started. To understand this, again we have to consider some vector field A, which is spread over some region, and if we consider any closed surface S, then we say that it would be enclosing some volume V. Now let's see what the theorem states. The theorem states that the normal surface integral of a vector field A. What is the meaning of normal surface integral of a vector field A? Surface integral. How do we write surface integral of a vector field? When we talk of surface integral, that means two dimensions are involved, so there would be double integral, right? And then we write it as A dot ds. And normal word here has a meaning, because you know that this is actually A dot n cap ds. We have done this because n cap is what? It is a unit vector which is perpendicular to the surface taken. So here if S is the surface, so n cap is definitely the unit vector which is perpendicular to that surface, because whenever we have to make use of integral, for surface we have two dimensions already available to us, but then this n cap gives us the idea of the third dimension, the height factor. So that's why it's always taken perpendicular to the surface. All right, and that's why we have written here normal surface integral, so that you should know that the surface integral basically involves the unit vector which is normal to the surface. All right, then it is saying over a closed surface S. So that means the surface that we have considered, it is a closed surface, right? So what do we write here? It is closed, so we are going to put a circle over here, and then we would mention that S is the surface that we are talking of. Alright, so this thing is clear. Then it says it is equal to, so we'll put the equal sign. It is equal to what? It is equal to volume integral of the divergence of the vector field A. How do we write now volume integral? We know volume integral involves all the three dimensions, so definitely we need these three integrals. And then it is saying volume integral of what? Of divergence of vector field A. So for divergence, we have to mention del dot A. And then since it is volume integral, so we have to mention that quantity with respect to which the integration would take place. So dV has to be there. As in surface integral, we mentioned ds. Okay. And then it says over the volume V enclosed by the surface. The surface S is enclosing the volume V. So we would mention V here. So this is the mathematical statement of Gauss divergence theorem. We write like this in words. This is the thing, this is the theorem, the exact statement you have to write, and this is the exact statement that I have just written. And mathematically, we can express this whole statement like this. Okay. Once again, I'm saying the normal surface integral of vector field A, so A dot ds, and then obviously the double integral over a closed surface S. So that's why we have put this circle over here and have mentioned that the surface we are talking of is closed one and it is S. And that is equal to, so we have put the equal sign, and then it's equal to volume integral of divergence of vector field A. So for volume integral, we need three integrals, and then integral is of divergence of vector field A, so del dot A. Obviously, we have to put dV, and then it is over the volume V, which is enclosed by the surface. So this surface S is enclosing volume V. That's why we have mentioned V here. The opposite of this theorem is also true. That means if we start with something which is a volume integral, if we have volume integral of something and we take the divergence of that vector field over volume integral, then that would give us the surface integral of that vector field. So both ways it is possible. This leads to this and this leads to this also. So whenever we see anything like this, which looks like this, we directly write it like this by using Gauss divergence theorem. That's why I say that surface and volume, they are related, because whenever there would be surface S, it would be enclosing some volume V. And whenever we find something like this, which is del dot A and then dV, like volume integral of divergence of some vector field, then we can easily write it as A dot ds, because definitely that vector field A would be enclosing some closed surface S. Only then it is possible that that particular closed surface is enclosing some volume. Now let's see the proof of it. For the proof, we have to consider some vector field which is spread over the region. Here we say that a closed surface S is enclosing a volume V. Actually, you can imagine that the vector fields are spread everywhere. Vector fields are spread. See, I have shown the vector fields by orange arrows. So it is spread over the entire region. And then we are considering some closed surface in this region, okay, which is enclosing some volume. And that volume is V. This whole surface S is enclosing some volume V. And then we have divided that volume. As you can see, I have written in the proof that consider a closed surface S enclosing a volume V. Obviously, this surface is enclosing some volume, but that volume has been divided into very large number of elementary volumes. That means very large number of small volumes in the form of cubes or rectangular parallelepipeds adjoining each other. So either we can draw cubes here, or we can draw rectangular parallelepipeds, which are basically cuboids. So here you can see that we have drawn cuboids. So basically the whole surface is enclosing some volume, which is volume V. Now here you can see this entire volume has been divided into large number of small volumes. So as you can see, we can draw even more cubes or cuboids here just to show. So I have drawn all these to give you the idea that how this surface is enclosing some volume V, and we are considering that particular volume here. So that volume V is further being divided into large number of small volumes. So you can see this number 1, number 2, 3, 4, then 5, 6, 7, 8, 9, 10, 11, and like this. We can draw as many volumes, small volumes as possible. So electric field is spread over the region. This electric field is A basically, which is spread over the region, and then we have considered some closed surface S, which is enclosing volume V, and that volume has been divided into very large number of small volumes because we can't deal with that entire volume in one go. We always make use of some small, we just pick some small element, some small volume, and then we try to integrate over the entire region. So this is what we have done here. So there are so many small elementary volumes which are there inside that bigger volume V, and then we would pick a particular volume and try to solve the whole derivation with that. So there it's written that consider one such cube or cuboid of volume dV. So this colored one is the cuboid that we have picked out of all those which are present, with its sides along the three axes x, y, and z as dx, dy, dz. So this small cuboid has volume dV, and then as you can see, we have drawn the x, y, and z axis. So it would be having its sides along x-axis as dx, along y, dy, and along z-axis dz. So this is how we have picked one such small volume out of the entire volume. So vector field is spread. We have considered some closed surface S, which is enclosing some bigger volume V. Then we have divided that volume into large number of small volumes. And then for the solution, we would pick a particular volume. Okay. Now let's talk about that particular small volume dV that we have chosen. And you can see here that it has the sides as dx, dy, and dz along x, y, and z axis. A, B, C, D, E, F, G, H are the vertices of this cuboid that we have drawn. And again, the way we solved divergence in terms of Cartesian coordinates, we first try to see the whole picture along x-axis. We totally solved it, and then we got some result, and then for y and z we just wrote that similarly we would get the same result for y and z axis just by replacing x by y and z respectively. Here again we would use the same concept. We will solve for all the flux which is entering and moving out for the x-axis, and then again we would write it for y and z just by looking at the result which has been obtained for the x-axis. These are the vector fields, and again we can consider that vector A to be some velocity vector, velocity of fluid, which is just passing through this one side and going out through the other. To see the changes which are occurring along x-axis, we have to consider these two sides. You can see the side AEHD and the side BFGC. So these are the sides that we would consider, and we are saying that the flux is entering in from P1 and going out through P2. And you can see that this point A, if this point A represents the coordinates x, y, and z, then point B would be representing x plus dx, y, and z, because if you go from this A to B, only x coordinate is changing, there is no change in y and z. Similarly, if we pick these two sides, this particular side, then you can see that to move from this face, the left face, to the right face, the only difference that would occur would be along x-axis, and there would be no change along y or z-axis. You can easily see this. Since vector A has ax, ay, and az as its rectangular components along the 3D direction, and we would also consider that let ax at P1 be ax P1. So the value of ax at point P1 is ax of P1. We are considering only these two faces, left face and right face. And what are the area of these two faces? It's same. You can see this is dy, this is also dy, this is dz, this is dz, dz, and this is dy, this is dz, this is also dy. So the area of left face and right face is dy dz. Okay, so we can write down the flux through left face of the cuboid, and we can write the flux through right face of the cuboid. Let's write it down. As we discussed in our previous video, that divergence of any vector actually tells us the total outward flux per unit volume from the point that we consider. So it is total outward flux. So that's why whenever I have written flux, I have mentioned this outward flux specifically, because divergence actually means what is the outgoing flux. It always talks of outward flux per unit volume. So if we talk here about flux through left face and right face, for the left face, first just consider the values. What are going to be values? Now we know that since we are talking of the changes along x-axis only, because these left and right face, if you move from left face to right face, that's the direction of motion, then you will find that only the x coordinates would change. So if the value of x component, which is our ax at P1, is ax P1, so we would be having this ax P1, and then we can mention that let its value be ax P2 at P2. So here we have considered that the value of ax, because ax would only change, so at P1 its value is ax P1, and at P2 its value is ax P2. So flux through left face, the outward flux through left face would be having this value of ax, or whatever is the value of the x component, multiplied by the area of the face, which is dy dz. You can see here dy dz is the area of the left face, and similarly for right face also we know that dy dz is the area, and the value of ax is ax P2. So we can mention here ax P2 dy dz. Now just take care that I just mentioned that flux is the outward flux that we talk of. Whenever we talk of flux and whenever we talk of divergence, it takes care of the outward flux. Now through right face, we know the flux is moving out. But through left phase, the flux is moving in. You can see we have drawn the arrows like this, and we are just showing the direction also. Direction of the vector is that it is going from left phase to the right phase. So here, it is the inward flux and not the outward flux. For right phase, it is the outward flux because it is just moving out from this cuboid. But for left phase, the flux that we have written, that is the incoming flux, the inward flux. So, but we have to write the outward flux. So for that, we are going to put a negative sign here, just to show the opposite direction, because we are concerned with outward flux, but for left phase, we have the inward flux. So we will put a minus sign to represent the outward flux, because when we talk of directions, magnitude is same, only direction is changing. So for the change in direction, we put a negative sign. We just change the sign. Okay, so we have found all these flux, and now we can also tell what is AXP2. If you have seen my previous video, divergence in terms of Cartesian coordinates, you can understand that. Let me show you a glimpse from the previous video. Here, this is the derivation from the previous video, divergence in terms of Cartesian coordinates. This is what we did. And here you can see we considered 3 points basically. There was Q, there was P, and there was R. So to find the value from P to R, the change in Vx, we wrote that whatever change is in Vx with respect to x, because the change that we were considering was only along x-axis. And then there was dx by 2, because this point P is lying in the middle of the cuboid. So, and the length of this cuboid is dx, right? So that was the reason. And then the value of x component at center CDEH, that means at R. So the value at R we considered was the value at P plus whatever change has happened in between, right? So value at P was Vx, and then the change that happened when the vector was moving from P to R was this particular thing, curly Vx by curly x dx by 2. So same formula, same method we are going to use now. Here there is no middle point. We have just 2 points, P1 and P2. If we know the value at P1, we can find the value of at P2 only if we know what is happening in between. So we are concerned with what is happening in between when it is going from P1 to P2. So let's write down. So AXP2 can be written as the value at P, which is AXP1, and the change that is happening. Now what is the change happening? Change is happening only in AX, and that too with respect to x. And then we know that what is the distance? Distance is dx, because that is the complete distance, the actual change in x, what is happening. So whenever we talk of change, we talk in terms of both. How much change in x coordinate and how much change in ax with respect to x. So both things we are going to mention. So first we'll mention what is the change in ax. So change in ax again would be curly ax by curly x. Now you know I have written curly because it is partial differentiation, because a vector is made up of ax I cap, ay j cap, and az k cap, and then they all are depending on x, y, and z directions. So we have to show curly. A is partially depending on x, y, and z. Okay, so this is the thing. So how much change in ax component, and then how much change in x coordinate, that we also need to mention, because it is, this thing also matters, that how much distance the vector has moved, what's the change in vector and how much distance it has moved. So that is represented by dx, simply dx. Since there is no center point, so we are not having any dx by 2. We are just going to take dx because we considered only 2 points p1 and p2. Okay, so we are done with this value. Thus we can write the flux through right phase, the outward flux through right phase, in terms of AXP1. See, we know we have already written what is outward flux through right phase, that is AXP2, that whatever is the value of AX at P2 multiplied by D by dz. But now we have found what is AXP2 in terms of AXP1. So I'm just going to write it down. So this becomes AXP1 plus curly AX upon curly X dx multiplied by dy dz. We have found the outward flux through left phase, we have found the outward flux through right phase. Now we have to find the net flux through these two phases, okay, this left and right phase. So how do we find net flux? It is by subtraction. So we'll subtract the flux through the left phase from the flux which is coming out through the right phase. So the flux through the phase BCGF is basically AXP2 dy dz, which we have written in terms of AXP1, and then the flux through ADHE, that is AXP1 dy dz. Now you know this is also AXP1 dy dz, so that will get cancelled and we are left with curly AX upon curly X dx dy dz. This is the same expression that we obtained in previous video, almost similar. There we considered our vector to be vector v and we were having vx. So this is almost same. The derivation is almost similar. And see, I am writing all the steps. See, I'm writing all the theory. So this is how you have to attempt it in exam. I have mentioned the statements, I've drawn the figure, mathematical statement, then the proof and whatever statements you need to write and how do you need to solve it. I'm mentioning everything. So you just need not to refer to any book or any other source. You just can simply watch this video and make your own notes and you're good to go. Again, we are going to use that similar stuff, that similar criteria, that if we know whatever change is happening along x axis, we can write down the change occurring along y and z axis. So we can find the net flux through the top and bottom faces and also through front and back faces. So let's write them down. Now for faces A, B, F, E and D, C, G, H, you can see the faces A, B, F, E. That means this bottom and top. Okay, so we can write down. So this change is happening along y-axis. See, in going from bottom to top, we have to move along the y-axis. So we can write this down. Simply replace ax by ay, and this would also be curly y, and these remain the same, dx, dy, dz. And now the flux through faces A, B, C, D and E, F, G, H. That means the front and the back faces. So you know now that if we have to move from front face to back face, then we have to move along z axis and there will be no change along y and x axis. So let's write down. This would be curly az with respect to curly x, curly z, and dx, dy, dz as it is. Since we have found the flux through all the faces, now is the time to find the total flux. So let's write down the total flux through this cuboid. We have to simply add all the fluxes that we have obtained. This is in terms of volume because we consider a small volume element, dV. But if we talk in terms of surface, then we mean that this flux is just going over the surface. So whatever surface is there, this whole flux is just going over the surface. So if we have to mention this in terms of surface, then we would write it as surface integral of vector A. This is equals to A dot ds, and this is S, the surface of cuboid we can write here, because the entire surface is S, but this thing, if we are talking in terms of cuboid, then we can say that the flux is moving over the surface of cuboid. So this thing can be expressed like A dot ds, but the surface here is surface of cuboid. You know that if you put any cuboid, say a brick, in water, you would see that all its sides, all its surface would get wet. So that means that liquid has gone through all the surfaces. So same is the case with vector field, because that we can consider a vector field to be some fluid vector. So this is why we have written this, and this ds is surface area of the cuboid. So all these field lines, they are just passing over the surface of cuboid, and I mean it is passing over the left face, it is touching the right face, top, bottom, front and back, all the faces are getting affected. So that would be counted as surface. You must know the meaning of surface and volume. So this is what we have obtained, but we also know what is the expression for divergence. We can write it down. We know that divergence of any vector, so if it's vector A, that is written as curly ax upon curly x plus curly ay upon curly y plus curly az upon curly z. This we already know. So what we can do is, here you can see we have all these terms present. This is curly x upon curly x, this is curly ay upon curly y, and this is curly az upon curly z. And all these three terms have this dx, dy, dz as common. And what is dx, dy, dz? That is volume, dv. So we can write this dx, dy and dz as dv, because it's showing the change in all the directions. This is the volume of cuboid. So if this highlighted portion represent our equation 1, and now we know what is the expression for divergence of vector A, and we also know what is dx, dy, dz, we can use these two things to write this equation 1 in a different way. Let's write it down. So this becomes A dot ds, and here the surface is surface of cuboid, and that is equals to del dot A dv. Okay, so this is the relation for cuboid only, the cuboid that we have considered. So this relation we have obtained for cuboid. So let me mention here for cuboid. But now we are not only concerned with this cuboid, actually we want to know the value over the entire region. And that's the reason that we divided the entire volume into large number of small volumes. And one such volume we picked was this cuboid dv. So to find the value for the entire region, what do we have to do? We have to integrate. So here we have the integration because this A dot ds is already there, but this is having the surface only of cuboid. This is involving only cuboid, but now we want to involve the complete surface F. And similarly here, this divergence of A and dv, this dv is only this particular cuboid, this small volume element that we have considered. But as I drew before, there were so many of them. So to account for the entire volume, we have to include all those volumes. So we have to integrate over the entire volume V when we want to include the entire surface S. So for that, what do is, here we have the integral already. So we cannot do that if we have an integral already and then we'll again put some more integrals. That is meaningless. Either we have single integral, double integral or triple integral, not more than that. And for area, if we are talking about surface, then only double integral. So this is there, but now I'm going to mention S because now we are considering the entire surface. And what would happen here? Now here this is for only the cuboid dV of volume dV, but now we want to find for the entire volume, so we have to integrate. So let's integrate. Since this is dV, so that means we have to include the triple integral. So triple integral is there, and then we would mention here the volume V. So this is the final expression, and this is our Gauss divergence theorem. This is the final answer. So this is the final result. And if you have to represent in terms of Cartesian components, then we can write it as, let me write it here. We would write all the components separately. So this integral would stay intact, and here this becomes, because this is a dot ds, right? So it's a dot product. And what is the answer of dot product? It's a scalar. So I'm directly going to write that the x component of a multiplied by x component of ds plus the y component of a multiplied by y component of ds plus the z component of a multiplied by z component of ds. So this is the thing, and that is equal to, again this volume integral would stay as it is, but now this del dot a, again we'll get some scalar quantity. And how does it look like? This is curly a x upon curly x plus curly a y upon curly y plus curly a z upon curly z. This is the entire expression, and multiplied by dx, dy, dz. This is the way of writing it in terms of Cartesian components. Whenever we talk of Cartesian component, basically what do we have to do is just split the vector into its x, y and z components, and that's it. So this is all about Gauss divergence theorem. We started with some surface which was enclosing volume V, then we divided the volume into very small number, large number of small volumes, and then we picked a particular volume element dV, and then we solved it. We solved for x completely, and then we wrote in similar fashion for y and z. Total flux, and then we used our divergence formula, combined both effects, gave us the Gauss divergence theorem. And then we also know how to write it in terms of Cartesian components. So if you find this theorem in exam, this is the way how you have to represent it. All the steps are mentioned, and you can follow this derivation. If there is any query, please do mention it in the comments box. That's all for today. In the next video, we'll try to discuss the physical significance of curl of vector function. Now we are done with divergence. Now curl is left. So we'll do that. That's all for today. Thank you.